Let me share my screen. But, let me take roll first before I do anything else. Okay, answer to your names, please. Cruz, Fonseca, Foster, Lanza. Here. Oliver. Here. Patel.
Here.
Retzlaff.
Yep.
Shaddix. And there's somebody who just joined online, Sneller. Let me see here. And Sneller is here. All right. So, what's your name?
Kevin.
Last name?
Fonseca.
Oh, yes. All right, so let's see. Don't think we started chapter 2. So that we're going to talk about now. All right, so the first thing we're going to discuss in chapter 2 are some laws as it relates to chemical reaction combinations and so on. And the first law is the law of conservation of mass, which basically says that in a chemical reaction, mass of the contents or the substances involved in the reaction doesn't change. In other words, whatever the total mass that you end up with in your products will be equal to the total mass of the reactants, right? So that's the law of conservation of mass. And there's a theory that is used to explain that and other things that we observe. But we're going to get into that later on. But before we do that, let me talk about another law, which is called the law of definite proportions, which says that all samples of a compound have the same composition. Another way of stating it is that all samples have the same proportions by mass of the elements present, right? So basically what we're saying here in this particular law is that if you have a compound and you break it down into its constituent elements, and if you look at the percentages, then those percentages will be fixed for that same compound, all right? A simple example of that would be water. Water, of course, we all know, is made up of hydrogen and oxygen. And the composition, if I remember correctly, is 89% approximately of any water sample would contain oxygen. And the rest, which would be 11%, again, approximately, would be hydrogen. And that is true regardless of where you get the water from, right? If you get it from, rainwater or from the sea or from rivers or from even outer space, the percentages would be the same if it is water, if it is the same substance, right? And here's another example of a different substance. I think this is copper, if I'm not mistaken, this is copper 2 hydrogen carbonate, and these are the breakdown of the percentages by mass. 57.48% would be copper, 5.43% would be carbon, 0.91% would be hydrogen, and the rest, which is 36.18%, would be oxygen, all right? And this is just highlighting the fact that it doesn't matter where you get the substance from, the compositions or the composition will be the same, all right? Okay, so let's look at this example. It says the mass ratio of oxygen to magnesium in the compound magnesium oxide is 0.6583 to 1. The question is asking what mass of magnesium oxide would form when 2.000 grams of magnesium is completely converted to magnesium oxide. So to answer that, we have to first use this ratio to find out how much oxygen was incorporated in the magnesium. So the way we're going to do that is we're going to start off with the 2.000 grams, and I'm going to multiply that by 1 gram. In fact, let me make a slight correction here. Let me just erase everything. I've made a correction. I'm sorry. So 2.000 grams of magnesium, and I'm going to multiply that by 1 gram of magnesium down here as a denominator, and up here I'm going to have 0.65831 grams of oxygen, right? Because that is the ratio of oxygen to magnesium in magnesium oxide, right? And the purpose of doing that is to find the mass of oxygen that reacts with the 2.00 grams of magnesium. So that would be 2.000 times 0.6581. And according to my calculation, this works out to be equal to 1.316 grams of oxygen. So to get the total mass of magnesium oxide, I'm going to add 2.000 grams to the 1.316 grams, and that would be the answer. So that would be 3.316 grams of the magnesium oxide compound. Yes, sir.
You did 6581.
Hmm?
How come you did 6581?
Yeah, there should be a 3.
Oh, 3. Oh, my bad. Okay, so that means I need to change. Let me see here. So 2 times 0.6583. So this should be, well, it doesn't change much. This will be 7 right here. So this will be 7 right here, which will be 7 right here. Okay, thank you. And that's how you do that. All right. Okay, any questions about this? Any questions? Any questions? Okay, excuse me, moving along. Another law which we need to talk about is a law known as the law of multiple proportions. Oops, what did I do? Okay, and this law is kind of wordy. Whoops. This is the law in words. It says when 2 or more different compounds of the same 2 elements are compared, the masses of one element that combine with the fixed mass of the second element are in the ratio of small whole numbers. So let me try to explain what this law is saying. What this law is saying is that if you have 2 compounds made up of the same elements, right? And if you get a certain amount of those 2 substances where the mass of one of the elements is fixed, then when you look at the mass of the other elements, when you compare them, the ratio between them would be some small whole number ratio, like 1 to 1, or, well, maybe not 1 to 1, but 2 to 1 and so on, all right? And I think I have an example here of comparing carbon monoxide to carbon dioxide, right? So they're both made up of the same elements, all right, carbon and oxygen, right? But they're obviously different compounds because their compositions are different, right? So what was done was that they decided to take a certain amount of each of them where the mass of the carbon is the same, right? 3 grams of carbon, right? And what you'll find is that the amount of oxygen that each of these will require to make their respective compounds is 4 grams in the case of carbon monoxide and 8 grams in the case of carbon dioxide. So you can see the obvious ratio between the oxygen that will react with 3 grams of carbon to form carbon dioxide compared to the oxygen that will react with 3 grams of carbon to form carbon monoxide. So there's obviously a 2 to 1 ratio here, which is basically shown by this calculation right here, all right? So the ratio of oxygen to carbon in carbon dioxide is exactly twice the ratio in carbon monoxide. And of course, that comes as no surprise because you have a subscript here of 2 in the case of oxygen in the case of carbon dioxide, and a subscript here of 1 in the case of the oxygen in carbon monoxide, all right? So that's basically what that law says. Here's another example. Now, it turns out that 28 grams of nitrogen can react with these amounts of oxygens, right? 16 grams to form one compound, 48 grams to form another compound, 64 grams to form a third compound, and 80 grams to form the fourth compound, right? So if you look at these masses here, for the same mass of nitrogen, you see that you can basically end up with a ratio of, if you divide right through by 16, you're going to get 1 here, you're going to get 3 here, 16 into 64 gives you what? 4 here and 5 here, right? So therefore, the ratio of the smallest whole number ratio will be 1 to 3 to 4 to 5 for the same mass of nitrogen for each of these compounds. And the actual compounds are these compounds right here. Dinitrogen monoxide, dinitrogen trioxide, dinitrogen tetroxide, and dinitrogen pentoxide. And as you can see here, if you look at the subscripts for oxygens in each of these compounds, they mirror the ratio that I just indicated up here, 1 to 3 to 4 to 5. All right, so that's another demonstration of the law of multiple proportions. Okay, so now we're going to get into some explanations for some of the things that we just looked at. And the explanation that was put forward first by this guy, Dalton's atomic theory, he was able to come up with this theory that explains some of the things that we discussed earlier. All right, so let's go into the assumptions of this particular theory. And the first assumption is that matter is composed of atoms, right? So there was a time, I think it was the Greeks back in the day, who came up with this notion of, what would be the smallest unit of anything material, right? If you could break down something into its smallest unit, what would that look like? And the Greeks had a term for it, they call it atomos. And if I remember correctly, it's the Greek word atomos means something to the effect of cannot be broken down any further or something to that effect, all right? So from that term, or from that Greek word, we have our term that we use now, which is the atoms, which would be the most smallest unit of matter, which according to Dalton's theory that he put forward, he suggested that these particles are tiny and indivisible, right? Now, let me just say that we now know that not to be true, right? We know that these particles are actually divisible. You can actually break them down into simpler particles, namely electrons, protons, and neutrons. And I'm quite sure we're all familiar with that, right? So this is just another example of a theory that was put forward, made sense at the time, especially given the limited technology that they had back in the 1800s. But now we know, again, based on experiments. In fact, we're going to discuss how we determine or how these particles were discovered when we get to chapter, if I'm not mistaken, chapter 7, right? So, so keep in mind that even though Dalton came up with that, we know that that is not true. Particles are actually divisible. Okay, the next assumption of his theory is that all atoms of the same element are identical, basically. So what he's saying is that if you could see 2 atoms of the same element, they will look identical. The next one is that atoms of different elements are will look different, right? So that's basically what he's in the third assumption. And then in the fourth assumption, compounds are formed when atoms of different elements unite in fixed proportions. And that explains why water, as I said before, has a fixed composition, all right? And then a chemical reaction involves a rearrangement of atoms. No atoms are created, destroyed, or broken apart. And this actually explains the first law that we looked at, the mass conservation law, right? If you remember, we said that the conservation of mass law says that matter is not created nor destroyed in a chemical reaction. And the reason why that is so is because at the fundamental particle level, the atoms themselves are not created nor destroyed, right? So basically, that's the reason why the mass is conserved in a chemical reaction. So just to further demonstrate how the Dalton's theory explains stuff like the conservation of mass and definite proportions and so on. So basically, we have some representations here of molecules of where we have 2 molecules of hydrogen here, we have 2 molecules of fluorine here, and the reaction that we're looking at here is a reaction where hydrogen will react with fluorine to form 2 molecules of hydrogen fluoride, right? So this is the equation for the reaction right here, right? And basically what this equation is telling you that one molecule of hydrogen will react with one molecule of chlorine to form two molecules of hydrogen fluoride. Now let's look at the situation we have here. What do we have here? We have three molecules of chlorine and we have two molecules of hydrogen. Now, based on the 1-to-1 ratio between the hydrogen and fluorine molecules, as stated in this equation, you'd expect that these two molecules of hydrogen will react with these two molecules of fluorine, which means that you're going to have one molecule of fluorine left over, which is this right here, and you're going to end up with 4 molecules of hydrogen fluoride. All right? So basically, the conservation of mass law is basically understood based on this particular theory, because the atoms are not created nor destroyed. The same number of atoms of each element is present before and after the reaction. And that includes the molecule that did not react. All right? Okay, so that's as far as that is concerned. Okay, so let's talk about what I mentioned before, the fact that the atoms themselves are not indivisible, they are divisible. They can be broken down into simpler particles. And I'm quite sure you're familiar with the subatomic particles. You have the protons and the neutrons, which are located at the center of the atom, which is called the nucleus, while the electrons are more dispersed around the atom. So this table here basically summarizes a couple of things, the locations of the particles and their properties, their fundamental properties, right? So these are the symbols that are oftentimes used to represent the different particles, proton, neutrons, and electrons. These are the symbols right here. And in terms of their approximate mass, what you'll find is that the proton and the neutron have about the same mass, while the electrons are significantly lighter, all right, as you can see here, right? So therefore, because the protons and neutrons are located in the nucleus, the bulk of the mass of the atom is due to the nucleus, right? Basically, the electrons, as I said before, are spread out around the nucleus, and they're lighter in terms of the mass, okay? In terms of their charges, what you'll find is that the proton will have a +1 charge. The neutron, as the term suggests, it's neutral, so it has no charge, and the electron has a -1 charge, all right? Okay, and then another term, again, this is something that you should be familiar with, isotopes, right? Isotopes are basically atoms, and you see it worded in different ways in different textbooks. One way of stating it is these are atoms which have the same number of protons, but different number of neutrons. That's one way of stating it. Another way of stating it is isotopes are elements having different mass numbers, all right? Which means that we have to define what we mean by mass numbers. But before we do that, atomic numbers. I'm quite sure you're familiar with that term. Atomic numbers are basically the numbers of protons present in an atom of an element, and each element has its own unique atomic number. So if you consult the periodic table, if I were to choose an arbitrary element like copper, if I'm not mistaken, copper has an atomic number of, am I reading that right? Is that
29.
29? Right. So copper is the only element in the periodic table which has an atomic number of 29, which means that it has 29 protons, right? Each element has its own unique atomic number. The mass number is different. Mass number, by definition, is the sum of the numbers of protons and neutrons present in the nucleus of an atom. Now, the mass number itself does not define an atom. It will define an isotope, but does not define an atom of an element, right? You can have literally 2 elements having the same mass number, all right? But you cannot have 2 elements having the same atomic number, because the atomic number is a unique property of an element. Okay, and based on the definitions of the mass number and the atomic number, we can easily determine the number of neutrons. All we have to do is subtract the atomic number from the mass number, and that gives us a number of neutrons. And that's basically it. Okay, so how do we represent or distinguish between isotopes using symbols? So we use this kind of represent, there are a couple of symbols actually. There's this one here, which in some textbooks, they call it the isotopic symbol, right? Where E is a symbol of the element. The mass number A is written as a superscript to the left, and Z, the atomic number, is written as a subscript again to the left, right? So for example, there's one isotope of chlorine which can be represented by this, right? So by looking at this, you can tell certain things about this particular isotope. You can tell the mass number, you can tell the atomic number, you can tell the number of protons, you can tell the number of neutrons, right? Now, that's one chlorine isotope, but there's another chlorine isotope, which is this one right here, right? So you see the difference between these two chlorine isotopes is the mass number, which means that they have different numbers of neutrons, right? The number of neutrons here in the case of chlorine in the case of chlorine 35 is 18, right? Whereas in this case, the number of neutrons here would be 20, all right? And as I said before, there's another way of representing isotopes. You can use this representation right here, or you can use this, Cl35, that is understood to mean the same thing, right? So you can use this representation here, but you can also use this representation, right? So doesn't matter which one you use. So here we have some questions here. This question is asking, how many protons are in chlorine 35? And the answer is what? How many protons are in chlorine 35?
17.
Exactly. Excuse me, how many protons are in chlorine 37? 17, exactly, same element, right? Each element has its own unique atomic number. And then it's asking how many neutrons are there in chlorine 37? I think I gave away the answer already, it's 18. All right? So basically, once you're given the isotopic symbol, then you should be able to, determine, the number of protons and neutrons and so on. Here's another example. How many protons, neutrons, and electrons are present in bromine 81? Now, in this case, they did not indicate the atomic number, but you still can find out what the atomic number is. All you have to do is consult the periodic table and look up the atomic number of bromine, which is what? I can see it from here.
35.
35, okay. So what would be the number of protons in the case of bromine 81?
45.
35, right? What would be the number of neutrons in the case of bromine 81? So in this case now we have to subtract 35 from 81, and that would be what? I got 46, all right? And then the number of electrons. Now, the number of electrons for an atom would be the same as the number of protons, right? So therefore, that would be 35 as well. All right? Okay. Let's see here. Okay, so now we're going to get into a discussion of another term, which is oftentimes confused with the mass number, right? And that is the atomic mass. Now, let me just remind you what the mass number is. The mass number, by definition, is the sum of the number of protons and neutrons in an atom, right? That's a mass number. The atomic mass is something different. The atomic mass is the mass, the weighted average atomic mass, the weighted average mass of the atoms of an element. And let me explain what we mean by that. Well, let me just say this first. So basically, we have to use the different units to measure, to express the measurements of very small particles, because the conventional units are not convenient for us to do that, right? So what was decided by the powers that be was that an atomic mass unit was defined, and that was defined as being equal to 1/12 the mass of a carbon-12 atom, all right? So basically what they're saying is that a carbon-12 atom would be equal to 12 atomic mass units exactly, right? And based on that definition, then we can determine and express the mass of other small particles like atoms and neutrons and protons and so on. So that's called the atomic mass unit. And it turns out that the relationship between the atomic mass unit and the gram unit is right there, 1.66 times 10 to the minus 24. And in the tables that I provided for you, which you'll have access to, of course, during your test, I have that relationship expressed in kilograms, which would be 1.66 times 10 to the minus 27 kilograms, right? So that's the atomic mass unit, right? Now, one thing that is mentioned here is that, and this might sound a bit counterintuitive, And that is that the mass of an atom is not exactly the sum of the mass of all the particles that are present in the atom. Now, that might sound weird, but that is actually true. And unfortunately, I cannot go into the discussion explaining that right now. But for those of you who have to do Chem 2, there's a chapter dealing with nuclear chemistry where this will be discussed, right? But for now, just accept it as fact that if you add up the total number of protons, neutrons, and electrons in an atom, that will not be equal to the mass of the atom itself. All right, there's a difference. There's a small difference between that mass of the atom and the mass of the particles in the atom. It's called the mass defect, and that's as much as I can say at this stage concerning that. Okay, so this begs the question now, do all isotopes of an element have the same mass? And the answer is no, right? Because isotopes have different numbers of neutrons, right? Even though the atomic numbers are the same, and even though the number of electrons are the same, but the number of neutrons are different. So therefore, different isotopes will have different masses, all right? So therefore, for a particular element, what you'll find is that, in fact, this is true for all elements, what you'll find is that in nature, there's a distribution in terms of the masses for a particular element. So in other words, if I were to have a sample of chlorine in a vessel, right? If I could separate out the isotopes, what you'll find is that the proportions of the different isotopes will be relatively fixed, all right? So that brings us to the concept of what I call the weighted average atomic mass, right? Because for any legitimate periodic table, such as the one that you see here, right? Each element has two numbers associated with it, right? One would be the atomic number, which, as we said before, by definition, is the number of protons. The other number that's associated with each element is the atomic mass. And this is oftentimes a source of confusion for students because most students, especially when they're learning this for the first time, assume that the second number is the mass number. It is not the mass number, it is the atomic mass. The mass number, let me remind you again, the mass number is the sum of the number of protons and neutrons in the atom, right? But the mass number is the weighted average atomic mass. And I'm going to show you how to calculate that based on this example right here. So this example is talking about the fact that you have two isotopes of carbon. Actually, you have more, but they're dealing with these two isotopes of carbon, carbon-12 and carbon-13. And what they have provided for you in this table is what is called the percent abundance. In other words, if you have a sample of carbon, 98.892% of it by mass would be carbon-12, and the rest would be carbon-13, all right? So this is basically constant throughout nature, throughout the universe, actually, all right? So how do we calculate the weighted average atomic mass? That's what this question is asking for. Now, in order for us to calculate that, in addition to this data right here, we're going to need the masses of the different isotopes. So they're given right here. The carbon-12 mass is 12.00050 after the decimal point AMU. And that for carbon-13 is 13.00335 AMU, all right? So, the way we'll set this up is, I'd start off with the mass of carbon-12, which is 12.00000 AMU, and I'll multiply by this number here, the percentage. Now, what I would do actually is multiply by the fractional abundance, which is the same thing, but expressed as a decimal number. So I'll multiply that by 0.98892, and I'll work that out. And I'll do a similar setup for the carbon-13 isotope. So this is the mass of the carbon-13 isotope, which is 13.00335 AMU times 0.01108. All right, so let's see what that gives. So 12 times 0.98892, and I'd have to round this off to how many sig figs? 1, 2, 3, 4, 5, 6 weeks. So 11.867 AMU, all right? And then for this one, 13.00335 times 0.01108. And according to my calculation, I got, in this case, I have to round off to 4 6 weeks, so that would be 0.4, I'm sorry, 0.1441 AMU, all right? So after I've done those two calculations, what I would do is add them up, right? So I'll add 11.867 to 0.1441, and the answer I would get down here is 12.0. Now in this case, I have to round off to 3 decimal places, so 12.011 AMU, all right? And that's basically how you get the weighted average atomic mass, right? So that number takes into account not only the masses of the isotopes, but the percent abundance, and that's how you do that, right? And that's how we get all those second numbers for each of the elements, right? So in the case of carbon, if you look at the periodic table and you look up the atomic mass of carbon, you're going to see 12.011. And basically, you're going to see similar numbers for other elements. And basically, that's how those numbers were determined. They take into account the masses of the isotopes as well as the weighted average atomic mass. Okay, any questions about this? Any questions? Any questions? Let me see if I can get you started on your next assignment. Assignment number 2. You. And this is for you. And somebody, Miss, okay, so somebody's out there in Zoom, which means that, which means that I have to publish that assignment for you out there. So let me do that now. So let me go here, go to files, and here. And I'm going to publish chapter 2. Okay, so Addison, you can now access assignment number 2. Now, for now, I want you guys to focus on questions 1, 2, and 3. And if you need any help, of course, that's what I'm here for. Okay, are we anywhere near finishing the first few questions? Yes, this one is kicking your collective behinds. Okay, let me help you out with this one. So this question says that copper is made up of two isotopes, right? And it says, given copper's atomic weight of 63.546, what is the percent abundance of each isotope? And it gives you the atomic masses of copper 63 and copper 65. So, what we can do is say, let me turn this on first. So what we can do is say, let X equal to the abundance of copper 63 and Y is equal to the abundance of copper, it should be Cu, of copper 65, all right? So basically, based on that, we can say that the atomic mass, which is 63.5, okay, so we can say that 62.92296 AMU multiplied by X plus 64.9278 AMU, that sum times Y, I should say, that sum is going to be equal to this right here, which is 63.546 AMU. All right, oops. AMU, all right? So here we have an equation with two unknowns, right? So I remember back in the dark ages when I was in high school, in order for us to solve an equation which has two unknowns, you're gonna need two equations, right? Back in my day, they used to call it what? Simultaneous equations, all right? So this is one of them. Now, my question to you is, what do you think the other equation is? Let me give you a hint. There are two isotopes. So what do you think the other equation is?
Where'd you make the other one, the X?
Hmm?
You do like, do your abundance, would the X be the abundance of 65? No.
Oh, that's what I said. No, I said X is the abundance of 63, copper 63, and Y is the abundance of copper 65. So based on those two, this is the equation I end up with, right? But I was saying that because there are two unknowns, you need two equations. This is one of them. So my question to you is, what do you think the other equation is?
Y equals.
Yeah.
I'm sorry?
You can go ahead.
Y equals 1 minus x.
Yep.
Okay, I was about to say X plus Y equal 1, but you're right, same thing, right? Y is equal to 1 minus X, right? So what you can do, where Y is here, we can put 1 minus X there, right? So you're gonna end up with 62.926 96 AMU. In fact, let me make things simpler. Let me cancel out the AMUs. Just rewrite this here. So 62.926 X plus 64.9278. And then I'm going to multiply that by 1 minus x, and that will be equal to 63.546, right? So all we have to do now is solve for x. So 62.926x plus 64.9278 minus 64.9278x, and that will be equal to 63.546. Okay, so I'd group the like terms, which would be the 62.926x minus 64.9278. So 62.926 minus 64.9278 x. And what I'm going to do is I'm going to subtract this from both sides. So you're going to end up with 63.546 minus 64.9278. 9278. All right. So I'm going to need more space. So let me just erase up here. Okay, so let me do the calculation for this part right here. So that would be oh shoot, okay, I made a mistake. This should be 62.9296. 96. Okay, so 62.9296 minus 64.9278. So that part works out to be minus 1.9982. And that will be equal to the difference here, which would be 63.546 minus 64.9278. Oh, and by the way, this should be an x right here. And this part, according to my calculation, works out to be minus 1.3. Hold on, is that right? Yeah, 1.3818, right? So therefore, x would be equal to minus 1.3818 divided by minus 1.9982. So let's see what that gives. Divided by 1.9982. So according to my calculation, round it off to how many sig figs? 1, 2, 3, 4, 5 sig figs. This works out to be equal to 0.69152. Oh, I just realized something. I made an error here. This should be rounded off to 1.382. And the reason why is because this has 3 decimal places, this has 4. So when you subtract that, this should be rounded off to 3 decimal places, which means that I need to change this here. A2. So let me do that again. 1.382 shouldn't differ by much, divided by 1.9982. So I got 6.6916. So 4 sig figs. Okay, and that would be the abundance of copper 63, and therefore for Y, that would be equal to 1 minus 0.6916. and I got 0.3084. Right? So therefore, we can say, let me just write the answer here, the final answer, the percent of copper 63 is equal to 69.16%, and the percent of copper 65 is equal to 30.84%. And that's how that is done. All right? Okay, any questions about this one? Any questions? Any questions? All right, let's continue with the PowerPoint. Let me clear this first. Well, let me give you, can I clear this or? All right. Okay, so let's go back to the PowerPoint. Okay, let me just say something about the periodic table. We're going to get into the periodic table in more detail later on, but this is just some introductory stuff about the periodic table. So the first person to come up with a periodic table is a guy, or was a guy by the name of Mendeleev, a Russian chemist. In fact, if I'm not mistaken, he's the most famous Russian chemist known. And basically what he did was that based on the known elements, I don't remember exactly, but this was a couple of centuries ago. Based on the known elements at the time, he basically arranged the elements on a sheet of paper according to their chemical properties. So basically back then, there was no concept of the atomic number, right? Because back then people didn't know what the structure of the atom is. The only thing that people could go by was the atomic mass, right? So what he did was that he arranged the elements in order of increasing atomic mass. And then what he discovered was that after so many elements, their properties repeat themselves, right? So he started off with, one row first, and then when the properties start to repeat themselves, he started off with another row and so on, right? And basically he ended up with groups and periods. The groups would be the columns, the periods would be going across in that particular table. One interesting thing about his version of the periodic table was that there are certain gaps that were existed in his table, which basically represented elements that were not yet discovered, right? But based on the position of these gaps, he could make certain predictions about the properties of these elements. And this is without any understanding of how the properties are arrived at. Because again, back then they didn't know anything about the atomic structure. They didn't know anything about the fact that it is, for example, the electrons, and more specifically, the valence electrons that determine the properties, which we're going to discuss later on. But back then, nobody knew that, right? All he saw was this pattern, and that was it, okay? So this was his version of the periodic table. Oh, 1869, that's when he came up with his version of the periodic table, right? And there's some question marks you see here, which represents elements that were not yet discovered. Just to give an example of an element that was not discovered back then, but he made certain predictions about it. And then when the element was actually discovered, you see that there's a close correlation between what he predicted and what the properties of this particular element actually is, right? So basically, the element that we're talking about here is now known as germanium, but back then he called it ecosilicon, all right? So this is what he predicted in 1871, and this is what was discovered in 1886, right? So the first thing that he predicted was that the atomic weight would be 72 grams per mole, right? As you can see, 72.6 is of course very close to 72 grams per mole. He predicted that the density would be 5.5 grams per cm cube. 5.47 was the density that was discovered for germanium. He predicted that the color would be dirty gray, and it was observed that the color is grayish white. Personally speaking, I don't know what the difference between the two, but anyway. And then the density of the oxide of this compound was predicted to be 4.7. turns out to be 4.703. He predicted that the boiling point of the chloride would be below 100 degrees. I guess he couldn't predict to a high degree of certainty. Turns out to be 86 degrees when this chloride was discovered. And then he discovered, or he predicted, that the density of the chloride would be 1.9. It was discovered to be 1.887. So you see here that there's a close correlation between what was observed when germanium was discovered and what was predicted before germanium was discovered. And this is not the only example. There are several examples where you see a close correlation between what is predicted and what was eventually discovered for other elements. Okay, so this is the periodic table, right? And there are several categories of elements that one can identify based on the positions of the elements in the periodic table. Most of the elements in the periodic table are metals, right? And these basically exist to the left of the periodic table. There's a zigzag line here, which basically represents a line of demarcation between the metals and non-metals. Most legitimate periodic tables will have that. And then to the right of the periodic table, you're going to have the non-metals, all right? Now, there is a minority group of elements that is located exactly on one side or the other of that line, and these are known as metalloids. Metalloids are basically elements which has some characteristic or properties in common with metals and others in common with non-metals, all right? So those are three broad categories. Well, there are some other categories that we can identify within the periodic table, but we won't get into that now. Let's move on to a discussion of molecules, which again, something you should know about. A molecule is a group of two or more atoms held together by covalent bonds, and the molecular formula basically gives you the information as to the number of atoms of each kind in a molecule, all right? That is different from the empirical formula, right? The empirical formula gives you the simplest ratio of the different elements, of the atoms of the different elements in the compound or in the molecule. So just to give you a different, an example of a difference between the empirical formula and the molecular formula, what we see here is the molecular formula for hydrogen peroxide, right? Basically what that formula tells you is that for every molecule of hydrogen peroxide, you have 2 atoms of hydrogen and 2 atoms of oxygen, right? The empirical formula gives you the simplest molecular ratio or the atomic ratio between the different atoms in the compound. So as you can see here, the empirical formula for hydrogen peroxide is simply HO, all right? So here we are given the molecular formula for octane, C8H18. So what do you think the empirical formula for octane is?
C4H9.
Mm-hmm. C4H9 is indeed correct. Very good. Okay, there are other representations that is used depending on, you know, your field of study, what you're trying to accomplish. What you're looking at here on the screen are 2 representations. The one on the left is called the ball and stick model, right, where the balls represent the different atoms and the sticks represents the bonds. And this is particularly useful, again, for those of you who have to do organic chemistry, you'll be using this quite a bit, because what you're going to find in organic chemistry is that a lot of reactions and properties displayed by molecules in organic chemistry or organic molecules is based on the 3-dimensional arrangements of the atoms. So therefore, in organic chemistry, what you're going to find is that it's very important for you to get a feel for the 3-dimensional shape of the molecule, because based on the shape, you can make certain predictions as to certain reactions taking place in some instances and other reactions not taking place, right? So it's kind of important for you to have that kind of appreciation for the 3-dimensional shape of the molecule. So that's a ball and stick model. Now, the diagram on the right is what is called a space filling model. To be perfectly frank, I don't think you'll be using this a lot in organic chemistry. That is usually used in higher level research, right? Because especially when it comes to, for example, pharmaceutical chemistry, because let's say, for example, a drug is being investigated to see whether or not it is, of some use therapeutically. A lot of drug interactions is a function of a couple of things. One would be the shape of the molecule, and two would be the size of the atoms in the molecule, right? Because very often when a molecule, which is a drug, is interacting with biological systems, it has to fit into what is called an active site, right? And that active site has to be of a particular shape that can accommodate that molecule. So therefore, the researchers who are investigating these sort of drugs, they take into account the shapes of the molecules and they take into account the size of the atoms that are involved so that you can have, the perfect fit when you have the molecule docking into an active site, right? So you may see this in biochemistry. If you plan to do medicine or pharmacy, you more than likely will see this. If you plan to do pharmaceutical research, you definitely will be using these sort of representations to help you in your research work. Okay, so this is representing acetic acid. Just to explain, going back to this ball and stick model, the usual convention in organic chemistry is that the black spheres or the black balls represent carbon and the white spheres represent oxygen. And then you can use different colors to represent other atoms. In this case, I'm sorry, did I say oxygen? I meant hydrogen. The white spheres represent hydrogen, right? And the red sphere in this case represents oxygen, all right? And you can use different colors for other atoms. Okay, so let's get into, just check something here. So let's get into nomenclature, which of course is dealing with how we name compounds. And basically, that's important, right? Very important in chemistry for us to know the rules, right? Now, the rules were developed by an organization within, an organization called the International Union of Pure and Applied Chemists, IUPAC, all right? And there's a specific division within that organization whose sole responsibility is to come up with rules for naming compounds, right? And I don't remember how often they meet, but they meet something like maybe 2 times maybe every 2 years or 3 years or something. I don't remember exactly. And they have to meet because every year new compounds are being made, right? And very often what happens is that the current rules may not be such that it can accommodate naming these new compounds. So every so often they have to meet in order to come up with these or change rules or come up with new rules to accommodate these new compounds. So this is the organization that basically came up with the rules that we're about to get into when it comes to naming compounds, all right? As stated here, it's necessary for us to have these rules because, of course, you can imagine it's very inconvenient to name the, to learn and memorize the names of different compounds if we did not have these rules, right? As stated here, you have 500,000 different inorganic compounds at least, and 20 million organic compounds. So of course, it's better for us to have these rules which help us to deal with naming these compounds, right? So this method is systematic, all right? And it goes for naming compounds if you know what the formulas are and vice versa, okay? So the first type of compound that we're going to look at are what are known as binary molecular compounds, right? Now, molecular compounds are basically compounds that are made up of non-metallic elements, right? So you're talking about non-metallic elements, and it's binary, which means that there are 2 of them, right? So we're talking about 2 non-metallic elements coming together to form a compound. So there are some rules that you need to remember. Okay, so the first rule is that the name consists of 2 words, right? The first word would be the name, the first element that is in the formula, the name of that element, all right? So the first element in the formula, you put the full name or write down the full name of that element. Now for the next element, you don't write down the full name, you're going to write down the stem of the name of that second element, and then it ends with IDE, IDE, all right? So the first name of the element, or the first name in the formula, the full name of that element, But for the second element in that formula, you're going to start out with the stem of the name of that element and then IDE, all right? And then in addition to that, you have to use prefixes which indicate the number of atoms of each element present in the molecule, right? And there's some prefixes which I think I have. Okay, I'll show you the prefixes later on. Now, the question now becomes, which element is first in the name or the formula? Now, you could memorize this chart, which I'm quite sure would be a bit of a pain, but basically what it comes down to is how the elements are positioned relative to each other, right, in the periodic table, right? So if the element is further to the left and down in the periodic table of the two elements, then that element is mentioned first, right? If the element is to the left and down, right, compared to the other one in the periodic table, then that element is named first, right? And then the other element is named after that, okay? So that's a rule of thumb. So for example, let's say you have a compound formed between arsenic and sulfur. Which of these two elements would be named first? All you have to do is consult the periodic table. Which one is to the left and down compared to the other one? Arsenic, exactly. Arsenic would be the one that's named first. Okay, so these are the prefixes that you need to know, because when it comes to naming binary molecular compounds, you have to indicate the number of atoms of each element. Now, there are a couple of exceptions that I'm going to point out, all right? But first, let me talk about the prefixes. So, and I'm quite sure you're familiar with these prefixes: mono for 1, di for 2, tri for 3, and so on, all the way down to deca. You can actually go beyond 10, but at our level, we just stop at 10, all right? So these are the prefixes that you need to know. Now, how do we use the prefixes? Now, there's a couple of exceptions where you don't use the prefixes. So let me see if I can squeeze it above here, one of the rules, and that is if the first element has only one atom represented, then no prefixes is used for that atom or used for that element. All right? So that is the first exception to the use of prefixes when it comes to naming binary molecular compounds. If the first element has only one atom represented, then you do not use any prefixes for that element. Now, the next exception, I'm going to see if I can squeeze it down here. If the first element is hydrogen, then no prefixes are used whatsoever. No prefixes are used in the name of the compound. All right, so basically what we're saying here, name of the compound. So basically what we're saying here is that if hydrogen is the first element in the formula, right, then you do not use any prefixes at all for the entire compound. All right, and we're going to see some examples of that, right? So in this chart here, there's some examples to the right of this table, which shows how to name these compounds, right? So if we start with the first one, okay, NO, right? That's a formula, right? So according to the IUPAC rules, the name of this compound is nitrogen monoxide. So you'll notice that for the nitrogen, there are no prefixes. Why? Because there's only one atom of nitrogen and it's the first element in the formula, right? So we do not use the mono prefix for the nitrogen because there's only one atom of nitrogen present and nitrogen is the first element in the formula, all right? But we do use a prefix for the oxide, the monoxide, right? Because there's only one oxygen atom present, but that's a second element, okay? So therefore, the full name of this compound is nitrogen monoxide. Okay, let's talk about the next one. Nitrogen dioxide, because again, you have one nitrogen atom, so therefore we don't use the prefix mono, but we have two oxygen atoms, right? So that's why we use dioxide to indicate the number of atoms of oxygen present in this formula, all right? Now, in the case of the third one, it is dinitrogen trioxide. Now, in this case, there are two atoms of nitrogen. So you do need to indicate the number of atoms of nitrogen by using the di prefix, right? And then tri, of course, would be the prefix for the oxygen because there are three of them. So therefore, we say tri and then oxide, and that's it, right? And in this case here, it's dinitrogen tetroxide. And in this case here, it's dinitrogen pentoxide, right? So that's basically how we name it. Now, in the case of this one here, SF6, you notice again, sulfur is the first element which has only one atom in the formula. So again, we do not use the mono prefix. So therefore, the name of this compound is sulfur, and then hexafluoride. Hexa because we have six fluorine atoms in this molecule, right? And if you understood what we just said, then you should be able to appreciate and understand how the others are named, right? So just to recap, we have to use prefixes, right? Because the prefixes are important in terms of indicating the number of atoms of each element present. However, there are exceptions. One, if the first element in the formula has only one atom, then you do not use a prefix for that atom, right? Two, if hydrogen is the first element, and we're going to see some examples of this later on, if hydrogen is the first element, then there are no prefixes used at all in the name of the compound based on the formula, all right? We're going to see some examples of situations where hydrogen is involved later on. Okay, so let's see if we can do these examples. It says, write the molecular formula and name of a compound for which each molecule contains 6 oxygen atoms and 4 phosphorus atoms, right? Now, the first thing we'd have to ask yourself is, which element would go first? Let's deal with the formula first and then focus on the name after. So if we're writing down the formula for this compound, which element, the phosphorus or the oxygen, what did I say about determining which element will be written first? The one is the one that's further down and to the left, right? So that would be which one in this case? Phosphorus, exactly, right? So basically the formula for this compound would be P4 and then O6, all right? So the next question we have to answer is, what's the name? So what do you think the name of this compound is?
Tetraphosphorus.
Tetraphosphorus,
Decoxide.
decoxide. And let me just say something here about decoxide and some other names of that type. According to IUPAC, you can say decoxide, but you can also say decaoxide, right? So according to IUPAC, you can say decoxide or you can say decaoxide. And the same thing is true for pentoxide and pentaoxide, hexoxide and hexoxide. So, IUPAC is very flexible when it comes to that kind of situation. All right, very good. The second example, A, you're to write the molecular formula of phosphorus pentachloride. So what do you think is the formula for phosphorus pentachloride? A. Well, So what's the formula for phosphorus pentachloride? That should be easy.
PCl5.
Exactly, PeCl5. Okay, and then the B part, they're asking for you to name this compound, S2F10. So what do you think the name of this compound is? Well,
Disilicon.
disulfur, oops, disulfur, and then what? Deca,
Fluoride.
exactly. And that's it. What time is it? Oh, okay. And that's it. Disulfur, deca, fluoride. Okay. So now we're going to get into naming ionic compounds. All right. So again, you all should know what ions are. An ion is formed when an atom either loses or gains an electron. And key thing you need to remember about ions is that when you have an atom losing or gaining electron, the number of protons do not change, which means that you're dealing with the same element, you're just dealing with a different form. All right. So of course, you know that there are two types of ions. You have cations, which are positively charged, and anions, which are negatively charged. All right. So what you'll find is that when an ionic compound is formed, it does not form discrete units as in the case of molecules, right? So in the case of a molecule like H2O, you have discrete units of 2 hydrogen atoms and 1 oxygen atom, right? In the case of ionic compounds, you don't have that, right? What you have instead is something looking like what you see on the screen in the case of the example of sodium chloride, where you have a regular arrangement, a lot of repeat units that just continue on and on, all right? And basically, because of that, there's no such thing as a molecule of sodium chloride, for example, right? In fact, we do not use a molecular formula to represent the composition of sodium chloride. We simply call it a chemical formula, which is basically an empirical formula because it gives you the ratio of the ions present, right? So that's basically what happens in the case of an ionic compound. So when it comes to naming them, the rules are a bit different compared to the names of binary molecular compounds. Some trends that we see here with respect to the positions of the different metals and the type of ions that are formed. So we're talking about the positions of the metals within the periodic table. So what you'll find is that group 1A metals, they tend to form a +1 charge ion. Group 2A metals, they tend to form a +2 charge ion. Aluminum forms ions that are +3 charge. And then when it comes to the anions, the negative ions formed from non-metallic atoms, their charges are respectively -3, -2, -1 for elements in groups 5, 6, and 7. All right. And then when you get to the transition metal region, things are a bit more confusing in that you can have situations where one particular element can form 2 types of ions where the charges are different, right? So for example, copper can form copper 1 and copper 2. Manganese can form manganese +2 and +4, and so on and so forth, right? So this begs the question, how do we distinguish between them, especially when it comes to naming compounds containing these ions? And there's a system that is used by the by IUPAC again. It's called the stock system. Basically, in the stock system, what you try to do, or what you do, is that you represent the different charges on the ions by using Roman numerals within parentheses, right? So I think I have some examples. Oh, I don't have any examples here. But like, for example, copper can exist as Cu2+, as well as Cu plus, right? So the name of this ion, according to the rules, would be copper 2 in Roman numerals in parentheses. And then the name of this ion would be copper 1, again, Roman numerals in parentheses, all right? So that's how we distinguish between those two compounds. I mean, those two ions, even though they're formed from the same element. Okay, so I feel that there's something I'm missing from this. Oh, so as stated down here, there are some transition elements that do not display more than one charge, right, in their ions. In those instances, you do not use Roman numerals, right? In fact, you do not use Roman numerals in the case of elements where it forms ions of only one charge. So like elements in group 1A, 2A, you would not use Roman numerals to indicate a charge, right? That's what IUPAC says. But for elements in a transition in a transition region that can display more than one charge, you need to indicate their charge using Roman numerals. All right, so there's something else. Can't remember it. Anyway, let's go to these examples. So, all right. So when it comes to writing down the formulas based on their names, how do we go about doing that? Oh, I remember now what I need to say. Very important. One big difference between naming ionic compounds and naming molecular compounds is that we do not use prefixes in the case of naming ionic compounds. All right? So the prefixes that you were using in the case of naming molecular compounds, like mono, di, tri, and so on, we do not use those prefixes when it comes to naming ionic compounds. All right? So very important. All right. So let's look at these examples. The first one is for you to determine the formula of calcium chloride. So how would you do this? Well, what you would do is look up the formulas for the calcium ion and the chloride ion. Of course, those will be available in the tables. So for the calcium ion, that's a formula. And for the chloride ion, that's a formula. Now, the key thing you need to remember is this, that the total charges must cancel out each other. In other words, the total number of plus charges must be equal to the total number of minus charges. As it is right now, that's not the case. So the question is, how do we achieve that? And that's very simple. All we have to do is put a 2 here, and now multiply the negative charge here by 2, which is equal to, in magnitude, the number of plus charges here. So the final answer, when you put these two together, will be Ca, and then this 2 becomes a subscript. And that will be the formula for calcium chloride. All right? In the case of B, magnesium oxide, again, we look up the charges, or we look up the formula for the ions. For magnesium, that's 2 plus, and for the oxide, that's 2 minus. In this case, we don't need to do any multiplication of anything because you have plus 2 here, which would equally balance out the minus 2. So in this case, the answer would be MgO, and that's it. All right? Now, that's the first part. The question in the second part is asking, what are the names of these two compounds, MgS? So what do you think the name of this compound is?
Magnesium sulfide.
Magnesium sulfide. Okay, so that's that. And what about B? CrCl3. Okay, so I hear somebody says chromium chloride. And if this was a 2-point question, you'll get 1.5. And there's a very important reason why. Because chromium is one of those elements in the transition region that can display more than one charge, right? There are 2 forms of chromium. You have +2 and you have +3, right? So which one do you think applies here?
+3.
+3, exactly. So that's the answer. All right? Okay, any questions about this? Any questions?
So when you say like the full name, would you just say chromium 3 chloride?
Exactly. Exactly. All right. So this is just showing you some of the monatomic ions. And of course, as we said earlier, there's some ions or some elements that can display different ions of different charges. As you can see here, you have titanium 2 plus titanium 4 plus, vanadium 2, vanadium 3, chromium 2, chromium 3, and so on and so forth. All right. There are some that don't do that, like silver, cadmium, and zinc. All right. But those in this region here and in this region here, they don't display more than one charge. All right. Okay. Okay, so let's talk about, actually, this is weird because anyway, let's talk about binary ionic compounds, which is what we were just talking about. They're made up of monatomic cations and anions. The combination must be electrically neutral, which is what we saw in the examples earlier. And basically, the formula unit is the simplest collection of cations and anions that represents an electrically neutral unit. So to write the formula, combine the proper number of each ions to form the neutral unit. We just did that. And then to name it, we named the cation first and then the anion. Oops. And very important, the monatomic anion names always end with IDE. Okay, so now we're going to get to what we call polyatomic ions. And as the name suggests, these are ions which are basically held together, represent atoms which are held together by covalent bonds, but that unit carries a charge, all right? And I think you can ignore this. I don't expect you to memorize the table I'm about to show you, which is basically a list of the polyatomic ions. Let me just skip all this here. So this is a relatively small list. I have 3 pages of more comprehensive lists of these ions, right? So what they all have in common is that it's a collection of atoms and that unit carries a charge, all right? And these are some examples here, and these are some formulas which contain polyatomic ions. So let's look at this question. Write the formula for the sodium sulfite and ammonium sulfate. So you guys will have access to the tables. As I said before, I don't expect you guys to memorize these ions, but what you find is that, with continuous use of these tables, you find yourself memorizing them, all right? So don't be surprised if that happens. So in the case of A, sodium sulfite, if you go to the table, you see that sodium has a formula of Na+, the sulfite has a formula of SO3, 2-. So again, the same principle applies. The total number of plus charges must be equal to the total number of negative charges. So we have 2 of these here. So therefore, when you put these together, you're going to end up with Na2, the 2 becomes the subscript, and then SO3. And that would be the formula for sodium sulfite. All right? Now, in the case of B, you're given ammonium sulfate, and you're to write down the formula. So if you go to the table, you'll see that the formula for ammonium is NH4+, and the formula for the sulfate is SO4 2-. Now, in this particular case, you're going to need 2 of these. You're going to need you're going to need 2 of these to counterbalance the charge of the 2- here. Now, here's where things are a bit different. When you're putting this together, this is how you do it. Open parentheses, NH4, close parentheses, 2, and then SO4, 2-. So you'll notice that the polyatomic, because there are 2 ammonium ions, and because it's polyatomic, in the formula, you have to put it or surround it with parentheses, and then you put the number of those ions outside as a subscript, all right? And that's basically how you deal with polyatomic ions, if you have more than one of them represented in the formula, all right? Now, in the case of the second set of examples, you're doing the reverse. They give you the formulas and they're asking for you to name these compounds. So if you go to the tables, you see that this is a sodium ion and this is a cyanide ion. So the name of this compound is sodium cyanide. Something you don't want to consume unless you're contemplating suicide, all right? So that's sodium cyanide. And then the next one, MgClO42. So if you look it up, magnesium would be the first name in the formula you write down. And then this ion, if you look it up, it's called a perchlorate ion. Perchlorate ion. So the name of this compound would be magnesium perchlorate, and that's how you name this compound. All right. All right. So if you go to your assignment, let's see what we have here. You're going to see that pretty much the rest of it has to do with, well, some of it has to do with writing down the formulas and so on, empirical formulas and predict the charges. But from question number 7 onwards, it's all about nomenclature, how you name compounds or name ions. So I will leave. Let me just see something. Oh. One more thing I need to talk about in the time that we have left. Oh, actually, all right, we have quite a bit. All right, we might not be able to finish everything. Let me talk about hydrates and then we'll call it a day. Now, hydrates are a special group of compounds in that they're ionic, but they have as a part of its composition a fixed proportion of water. All right, so that's why they're called hydrates. And the way we name them, well, there are two parts. You have the ionic part and you have the hydrate part, right? So to name the ionic part, we name it just like what we have been doing, right? But to include the hydrate part, you have to indicate the number of water molecules present. And again, you're going to use the same prefixes, mono for 1, di for 2, tri for 3, and so on. I want to see if I can find an example. Okay, so here's one example. So this hydrate here, and please note how we represent it. You have the ionic part, and then you have a dot, and then you have the number of water molecules, right? So the name of this compound would be barium chloride dihydrate. All right? And then there's this other one here. This is CuSO4.5H2O. So that's copper 2 sulfate pentahydrate, right? So that's basically how we name these compounds. All right? Okay. So based on what we have covered so far, you should be able to do questions. Okay, question 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, 13 you might not be able to do yet, so you can ignore 13 for the time being. 14, 15, 16. 16 is where we talk about hydrates. Actually, 16 and 17. And 18. So the only part that you can't do right now is the acids. We're going to talk about the acids next class. All right? Okay, so that's it for today. I'll see you guys tomorrow. Did I get everybody's attendance, by the way? What's her name? Foster. Okay. Cruz. Cadix. All right.
I have a quick question.
Yes, sir.
Do these safety goggles seem good enough for the lab tomorrow, or do I need to get there? I know,
Those are all right. Yeah,
those are
yeah.
good, all right, thank you. I'll see you tomorrow.
Yes, sir.
Hello, oh, what happened? Oh, we're doing the trick now?
Yeah.
Lou.
Sorry for Kelby emailing you. I didn't know that my first email went through.
Okay, you have to remember, because I've been getting a lot of emails lately.
I felt bad and wanted to apologize for that.
What was the email about?
The one I sent from the Canvas and then from Outlook,
About,
the same thing about changing the class.
oh,
I just felt bad for double
no
emailing
problem,
you.
no problem, no problem. That happens. Happens to the best of us. Okay, what am I doing here? Modules. Hmm. Okay, so now let me.